Hello, everyone, and welcome to another wonderful day of physical chemistry. So, today we're going to be kind of picking up where we left off with the kinetic gas model. So, we figured out a way to determine the pressure of a gas that behaves a certain set of ideal conditions in terms of velocity, amount, and uh, and volume. Now, the real trick here is trying to figure out the average velocity of a gas. So that's what we're going to focus in on today, and it's a bit of an involved topic. So, one of the first things that is very important to remember when we're talking about the properties of individual molecules, like velocity, instead of uh, bulk groups of molecules like pressure, is that we're not dealing with a single molecule. We're almost always dealing with a large number of molecules. So knowing the velocity of any given molecule is kind of useless. So what I'm going to want to really focus in on is the probability of finding a molecule with a given property. So specifically, if I say I want to figure out how many gas molecules, or what's the likelihood of finding a gas molecule, moving at, say, 400 meters per second, then I'm going to have to figure out what the distribution is and then look up the value for that specific point. So when trying to figure out the probability of a property, it's often very useful to start with energy. And uh, for the kinetic gas molecule model, we're assuming that the molecule only has kinetic energy, so no other form of energy. So I can go ahead and use Newtonian physics to say, all right, my total energy of this molecule will be divided into the translational energy in the x, the y, and the z direction. And then we can use our good old Newtonian equation that the energy in each one of those directions will be 1/2 mv squared, where we're looking at the velocity in those three cardinal Cartesian directions. And then we insert this into a rather fun postulate of physical chemistry, which is the Boltzmann distribution. So the Boltzmann distribution is simply an equation that says I can figure out the probability of a property using the energy of a molecule in that given state. So if I know the energy of a molecule with velocity v, I can figure out its probability. We only have to know three other things. The first of which is going to be the Boltzmann constant. So this is more or less the same thing as the ideal gas constant, but scaled down to a molecular level. So the Boltzmann constant can be given as the ideal gas constant divided by Avogadro's number. Then we have temperature. And you'll see why temperature plays an important role later, but it turns out that temperature is intimately related with the energy of a system. And then we have essentially a prefactor. So this is going to be a normalization constant, which we'll go ahead and deal with shortly. So what we can then do is, if I'm trying to figure out the probability of a molecule going a certain speed, then I'm going to want to use my energy equation in terms of those speeds. So I can go ahead and insert this equation into my Boltzmann distribution, and I get something that's kind of ugly. So what I can then do is make use of my exponential math rules and factor out each of these exponents to make a product of several different exponential values. And one of the reasons why this is going to be specifically useful is that I don't want to deal with this big, ugly equation right away. Instead, I want to break it down into a digestible chunk and say, I don't want to know the probability of a molecule going with any velocity. I'm just going to strip it down to the velocity in the x direction. So this lets me go ahead and just isolate my x term and say, well, my prefactor is going to change when I neglect these two terms. So I've got a new value, kx. So what we can then do is go ahead and deal with this prefactor term by using a rather fun bit of integration. So this is going to be my probability distribution of Vx, but it turns out that my gas molecule has to have a speed, which means if I um, integrate my probability distribution over all possible values, so my molecule can go any speed in between negative infinity and infinity, well, that has to be equal to 1. So what this really ends up helping show us is that this prefactor kx is what we call a normalization constant. What it really does is ensure that this property is upheld, that my molecule has to have a given speed. So before that, it turns out that the probability distribution is just proportional to this exponential value. And then by correctly solving for my kx value, or my normalization constant, I can ensure that these two expressions are equal. So in order to, actually have a real probability equation, we need to go ahead and solve for this normalization constant. So we can go ahead and solve this exponential term. This exponential form is what's called a Gaussian. It's when I have an exponential of a negative of my variable squared. It turns out that these can't be solved analytically. So I won't have a general form for the integral. Instead, I have to do some form of numerical evaluation, or it ends up being rather unique in that it has a solution from if I integrate from 0 to infinity or negative infinity to infinity. So you can go ahead and look up the answer for that integral in a textbook. So you will find the Gaussian integrals in the back of your textbook. We'll use them a lot more next semester. Or you can go ahead and look them up online, because there's a number of good online resources for some of these odder numerical integrals. So when we do that, it turns out that I get to pull out my kx value, and this inner term will end up giving me a value of 2 pi. So this is more or less a numerical value that comes from the integration. And then I essentially get the inverse of my prefactor here. So we get Boltzmann constant times temperature over the molecular mass of the molecule of interest, all to the square root. So this is all going to be equal to 1. So with a little bit of rearrangement, I get my general prefactor equation. So this gives us our normalization constant. So I can then plug this back into my full probability equation. And this gives me equation, so I know the exact probability of finding a gas molecule with any speed in a given Cartesian direction. So this same equation will apply for Vx, Vy, or Vz. And, and it's going to have a general Gaussian appearance, which we'll go ahead and illustrate shortly. But one of the important things to realize is that when we started, we were generally interested in the overall probability for the overall velocity, not just the velocity in the x direction. So we're going to need to do a little bit of finagling to go ahead and combine this probability distribution with the other 3 directions. And we can go ahead and combine these with making use of a classic trigonometric equation that my overall velocity will be equal to essentially the square root of the sum of the squares of my 3 directional velocities. We can go ahead and combine this with our overall probability distribution equation that we already made a little bit of use of. That the probability distribution for my overall velocity can be given as the product of my 3 velocity terms. And we already went ahead and showed this a little bit, but it turns out that logically, this is also going to have a dependence on the change in the velocity of the Vx, the Vy, and the Vz direction if I want to go ahead and say integrate this so I can make real use of my equation. So what I can then do is, since I know the equational form for Vx, I'm going to have an almost identical equational form for the Vy and the Vz. So I can go ahead and insert all of these equations. And each one of these terms will bring in a 1/2 m over 2 pi kt prefactor constant. So this gives me, when I multiply all three of them together, an overall 3/2 prefactor. So that's actually fairly useful. And again, this more or less just makes sure that my function is normalized. And then I have my old friend of my three exponential terms pulled together. And then, unfortunately, if I'm going to integrate this form, I'm going to have to solve a triple integral. And I'm pretty sure that nobody here likes to solve triple integrals. So it turns out that it's possible, using some knowledge from Calc 3, to go from a Cartesianal system to a radial expression by turning these Vx, Vy, and Vz directions and consolidating them down to just a simple dV. So this will give me more or less a similar form, except for my three exponential terms will now collapse down into one. And that's because turns out that Vx plus Vy squared plus Vz squared, so if I just add together these exponents, gives me V squared. That one's pretty straightforward. But I also have to worry about this 4 pi V squared term. And it turns out that this comes from a model of of conversion in between Cartesian and radial velocities, where more or less what I'm doing is I'm integrating over all of the radial terms. So I turn my extra two dimensions into more or less a surface area of 4 pi V squared with a thickness of dV. So more or less, that's where this extra conversional term ends up coming from. And then when I go ahead and combine all of these together, I get a rather simplified probability distribution for the velocity of a gas molecule, which is absolutely wonderful. And so what we find out that I will, in general, be more likely to have a higher probability at higher velocities. However, I'm also battling this dampening term of velocity here, which means that overall, my highest velocity will be at some sort of intermediate value. And this dampening term will essentially be greatest at low temperatures or high masses. So again, one of the things worth noting is that right now we are using a molecular basis where this is the mass of each molecule of my gas, and my Boltzmann constant essentially applies to individual molecules. However, we're chemists, we like working with moles and molar bases, so we can convert our molecular mass to our good old friend, the molecular weight or molar mass. So this is the classic value you look up in a periodic table. And we can go ahead and translate our Boltzmann constant to an ideal gas constant. So this gives us a nice general equation for the probability distribution of a gas. Now, I've now hit you over the head with a whole bunch of math. So let's go ahead and look at what this more looks like on a more visual basis. So specifically, we have a couple of levers we can tweak to change our probability distributions. So the first of which is going to be our temperature, and the second of which is going to be the identity or molecular weight of the gas I'm using. So let's start with this temperature idea. So temperature shows up a little bit in the normalization constant. So this is actually just going to, again, give me a little bit of this height profile just to make sure that when I integrate it, it gives me a value of 1. But more importantly, temperature shows up in this dampening function. So if I have a high temperature, it turns out that my velocity distribution is a little bit more spread out. Because again, with a negative value, high temperature gives me a large denominator, which gives me a relatively low negative value, which gives you a rather spread out distribution. At low temperature, this value is quite large, and an exponential to a negative large value gives you something that's quite small. So what we end up finding is that at high temperatures, my gas molecules are going to be able to obtain higher speeds and be more spread out. At low temperatures, my molecules are going to be moving much more slowly. So this is essentially the origin of the old idea and expression of temperature being a measure of energy, because this is really what we end up seeing here. High temperatures means fast molecules. Fast molecules means high energies. So a good way to think about when I'm talking about temperature is it is actually a fairly good stand-in for things like average velocity of the system I'm working with, or average energy. So this is actually a very important thing to keep in mind as we move throughout the rest of this year in physical chemistry, as we'll be using it a bit both semesters. The other important control we have is the identity of the molecule. So turns out that lighter molecules are going to be able to move a little bit faster. And that's because this energy that I provide in temperature is going to go less to kind of internal movements and trying to get the heavy molecule started and just more into straight speed. So lighter molecules tend to travel faster because turns out that they've got the same energy as these heavier molecules. It's just same momentum, same energy, same momentum, higher velocity, the smaller you are. So small molecules like an individual oxygen atom can fly around quite fast, while as heavier molecules like ozone will be a lot slower. So it's important to think about this as a constraint in how molecules will move around in the gas and atmosphere, is it's going to be very identity dependent. And this will have a lot of implications that we'll talk a little bit about more next time. However, one of the things that's fairly useful is, well, we don't always like working with probability distributions. I might want to condense this probability distribution down to a single number that represents, say, average velocity of a gas molecule. So let's go ahead and try and play around a little bit with this expression. So the first thing we might want to do is determine the average velocity of an individual gas molecule. So turns out we can use a nice little trick of calculus, where the mean of a value, or the average velocity, can be taken as the integral over all space. And now notice when we switched from Cartesian to radial coordinates, the velocity has to be positive. So I'm going to go from 0 to infinity, is going to be equal to the property I care about times the probability distribution integrated over my variable. So in this case, v times my probability distribution integrated over all possible velocities. So we can then go ahead and insert my equation. So I'm more or less doing the same integral I did before, except for now instead of v squared, I have a v cubed. Extra little expression comes in. Turns out, this is a Gaussian. I go to my integral tables, look it up, and find a mean value of 8 RT over pi molecular weight, all to the square root. So a nice general expression for the average velocity of a system. But it turns out that if you remember, what we originally wanted to determine was the average squared velocity, or the mean squared velocity, to make use of for our kinetic gas model. So in that case, I need to do this same general idea, except for now I'm doing v squared times my probability distribution, which gives me a v to the 4th expression, but otherwise everything's the same as before. Go back to my integral tables, look up a value, and I get an answer of 3 RT over the molecular weight. Woohoo! Gotta love it. However, Turns out if I want to compare these two velocities, I have to do apples to apples. So what I do is I go ahead and take the square root of my mean squared velocity, and I get the good old root mean squared velocity, or as some people know it, the quadratic mean, which is again a common friend uh, in a lot of mathematical averaging schemes. And it turns out that our two means are going to differ slightly, whereas my root mean squared is going to be slightly larger, and we'll get into the differences why in a little bit. Because it turns out there's another good number I might want to use to describe the average velocity of a system, and this idea of the most probable velocity. So you can think of the other two as looking at the mean. This is the median. So if I go out and I just sample the velocity of a gas sample, so go ahead and grab the air around me, figure out what's the most likely velocity I'm going to encounter if I have a velocity sensor. This is what we go ahead and try and determine. So if it's the most possible, this means that it's going to be a maximum on the curve. So the good old method of finding maximums is going to be taking the first derivative and setting it to 0. That means I'll immediately identify any maximums or minimums on my probability curve. So we can go ahead and start by taking the first derivative of my probability distribution. So it's quite nice. I get to pull out my prefactor. And in fact, I can even pull out my 4 pi expression. And what this is going to leave me behind with is the first derivative of v squared over e to the negative mv squared over 2rt. So at this point, we need to make use of a product rule followed by a chain rule in this exponential case. But it turns out that when we do this, exponentials, taking the first derivative, are always left alone. They'll just shoot out a prefactor. And so when we go ahead and do the first derivative, we're going to more or less have most of the points of interest sitting here in this central term, where we'll have 4 pi times the velocity plus, 8 pi times the velocity plus 4 pi times the velocity cubed times the molecular weight over RT. And it turns out that this is going to give us one of two possible solutions. Because again, remember, I want to divide by dv, so I should have a dv out here in the end, and then set equal to 0. So the first answer of how I get this whole expression equal to 0 is I literally put in a v value of 0. Well, that's the minimum, not the maximum. The other one is trying to set this expression to 0. And it turns out that this happens by plugging a value of 2RT over the molecular weight times the square root. And you can think of this as happening because I can factor out a v term here. So this is a lot of math really quickly, and it's probably been a while since you've done your derivatives in calculus. So feel free to repeat this step so you can prove to yourself how this works. But what we really want to focus in on is more of the visual consequences, because what I can do is map out my probability distribution for my gas, go ahead and more or less normalize it to a nice constant sense. And what we end up finding is that each one of these velocities tells me something a little different. And a lot of it comes down to the shape of my probability distribution, because a Gaussian has an immediate increase, hits some sort of maximum value, and then kind of trails off to infinity. And it's this trail that really makes a difference, because when I start with my most probable, that's fairly easy. It's at the maximum value. So this is, again, our square root of 2RT over the molecular weight. So again, what we're seeing is that the temperature and the molecular weight highly control what this most common velocity is. But because I have this high temperatures will essentially expand this exponential term, or this exponential decay, turns out that it's going to pull my mean a little bit further out. And that's what happens when we go from 2 to 8 over pi expression that happens here. And that's largely just factoring in how this exponential term drags my mean out. And then when I go to a root mean squared, because I'm squaring my velocity, it means that large values count more. And that's how we go essentially from 2 to 3. So this can be a really kind of important feature of the kinetic gas model. So if you remember, all of this was done to essentially figure out what our velocity was, so we could use this to finish building the ideal gas law. So it's been a while, so let's go ahead and bring all of our equations together. So first, what we really care about is our squared velocity, which we can also think of as our root mean squared velocity squared. So this is, again, our mean squared velocity. And we showed that this is equal to 3RT over the molecular weight, but we can also turn this into a molecular basis. So molar, molecular basis, fairly identical. Last time, we also showed that pressure times volume is equal to the number of moles times the molecular weight times the mean squared velocity. So what we can then do is, again, remember this is for the mean squared velocity in the x direction, which would be 1/3 of our root mean squared velocity squared. So we can go ahead and insert our squared velocity expression into here. And what we end up finding is a whole bunch of cancellation. So note that that we have two expressions of the molecular weight. We have to divide my velocity by 3 to account for just the motion that's hitting the wall, so the motion in the x direction. But this also cancels out for that same triplicate value that showed up in our root mean squared. So these all end up canceling out, and I get a rather simple expression. Pressure times volume equals number of moles times the ideal gas constant times temperature. Wait a minute, we just re-derived the gas law, but instead from first principles. But we get a lot of extra information along the way. And this is the big advantage of these ab initio or first principle models. They tell you a lot more about why your model works. So we can see a lot of this by looking at the average energy of a gas molecule, and that our average energy is going to be essentially built up on the translational energy in each given direction. So if you want to know what the translational energy is of a molecule, that turns out to be 3/2 times kT. Or if you want to know what the translational energy is of a mole of gas, it's 3/2 times RT. And what's actually really cool here is because the velocity depends on mass, but so does the energy, these contributions end up canceling out. So it turns out that the energy of a gas molecule has no dependence upon size, just upon temperature. So as long as you know the temperature of a gas, you know its kinetic energy. So I've been talking for a long while. Let's go ahead and review some key take-home points of this kinetic model. So first of all, note that the ideal gas law doesn't depend upon the identity of the gas. No dependence on structure, molecular weight, just on temperature. But it turns out that the velocity of the gas does depend upon the mass of a gas molecule, because essentially the heavier the gas molecule, the slower it hits, or the slower it moves, but the heavier it hits. So it has less energy and it's not moving as fast, but when it hits twice as hard as a gas molecule that's half as heavy, but moving twice as fast. So that's where we get a lot of this cancellation that results in this independence of identity for the ideal gas law. In addition, what we end up finding is that each degree of translation, so movement in the x, y, and z direction, ends up adding a half kT of energy. But it turns out that so do rotations. So if a molecule is a linear molecule and has 2 degrees of rotation, that means that it's also going to have an extra kT of energy. But if it's a uh, uh, nonlinear molecule, this means it's going to have an extra 3/2 kT because it's going to end up being able to have 3 degrees of rotation. And this actually ends up becoming fairly useful as we're going to go ahead and move on. So it turns out that a single atom is going to have 3/2 kT of kinetic energy. A diatomic linear molecule is going to have 5/2 kT, 3/2 in the translational, 1 in the uh, rotational. But almost every other gas is going to uh, have a full 3 kT of energy. And this is just a really cool set of phenomena that we can go ahead and make use of as we go into the future. However, I want to go ahead and next time we'll finish up some last key features of the kinetic gas model by using what we now know of the velocity of a system and look more at what this tells us about the interactions and collisions of gas molecules with each other. Till then, take care.